Hi, I'm Phil Bunting, and today I'm going to be talking about my work as a grad student in the Long Group at UC Berkeley. While I was there, I focused on transition metal single molecule magnetism, specifically on these low coordinate transition metal complexes. Uh, when I was at Ohio State as an undergrad, I heard a talk from Roald Hoffman on some chemical bonding in high pressure systems. And he said this phrase that really stuck with me, that we probe the extremes to learn about the middle. And I think that really encapsulates what basic research is all about. And so for me, this story is a story of extremes, both on the coordination chemistry side of things and the electronic and magnetic properties. But at least initially, this work is motivated by single molecule magnetism. And so just as a quick primer on what the properties we care about. Uh, so here we have the first reported single molecule magnet. It's a cluster of manganese ions, and their spins couple in such a way that we have a S equals 10 ground state. And because it has magnetic anisotropy, that ground state splits into M sub S microstates, which are split in energy. So M sub S is just a projection of spin along the molecular axis. And so what we have in this central picture, or the energy diagram, is there's an energy barrier between the up and down configurations of the magnetic moment. And as long as thermal energy is small relative to that energy barrier, then we can see slow magnetic relaxation, which is what we see in the hysteresis loops on the right. And additionally, we can also see effects of quantum tunneling. So those steps in the hysteresis loops are due to quantum tunneling of magnetization. And so single molecule magnetism is this interesting field where on the one hand, we see molecules displaying bulk-like properties such as magnetic hysteresis, but at the same time, they're molecules, and so they also show quantum effects. Now, like I said, I focused on transition metal complexes, and to understand the design principles that went into my work, it's important to understand how magnetic anisotropy arises in these systems. And so the top molecule here is a typical transition metal complex, and it has what we'd call quenched orbital angular momentum. Now, magnetic anisotropy is a direct result of orbital angular momentum. You can think about it as the movement of electrons around the positively charged nucleus creates its own magnetic field in the direction that's determined by the movement of the electrons. And so when we have quenched orbital angular momentum, we don't have any of the movement of electrons necessary for magnetic anisotropy. However, you can get some magnetic anisotropy just through excited state interactions. So that circled in red there, that down electron can move from the dx squared minus y squared to the dxy orbital. That excited state can mix into the ground state, and that can give us give back some of the orbital angular momentum that to a first approximation we had totally lost. Now, prior to my arrival in the Long Group, they had published this nice molecule. It's a dialkyl iron complex, and it takes this idea to an extreme where rather than depending on excited state interactions to engender magnetic anisotropy, let's just have a degenerate ground state. And the important feature here is that linear complexes are not affected by Jahn-Teller distortions. So circled in red there is the key component to having unquenched orbital angular momentum. That down electron equally sees both of those orbitals. And because it's a linear system, we're not going to remove that degeneracy with the Jahn-Teller distortion. And so what we have is unquenched orbital angular momentum, in this case, L equals 2. And so our magnetic properties are determined by the J equals 7/2 ground state, where J is total angular momentum. And the magnetic anisotropy in these systems can be orders of magnitude larger than for systems which have, to a first approximation, quenched orbital angular momentum. Now, when I started working, one of the things I was interested in pursuing was how to improve upon this iron system, because at the time that was the best transition metal single molecule magnet. And I had two papers to go off of. This one that I really like from an IBM, or a group from IBM. They put cobalt atoms on a magnesium oxide surface, And I was always a bit jealous of them because as a synthetic chemist, I was thinking that, what they did was they basically made a one coordinate cobalt ion or a cobalt atom. And so obviously this has, perfect symmetry um, and so, yeah, they saw incredibly large magnetic anisotropy, and the separation between the M sub j 9 half and 7 half states was 468 wave numbers. And then a bit later, actually a paper from our computational collaborators, where they put a cobalt atom into a known structure for an iron complex. And again, they saw this really large magnetic anisotropy. But additionally, both of them saw this, or both of them proposed this, this very unusual electronic ground state, which is a non-off-bow electronic filling. And this is more similar to what you'd see for lanthanide complexes. And so one of my main motivations was trying to make like an insoluble molecule that would have this electronic structure. And so the design requirements were pretty simple. We needed a cobalt-2 ion in a linear coordination environment, and it needed to have threefold symmetry to maintain the necessary orbital degeneracies. Now, the typical ligand that I would use for that, the tris-trimethylsilomethyl ligand, it just didn't work. And there's a paper from the Power Group where they also tried to make this complex, and they went on to use the phenyl derivative and were able to isolate this molecule here, which is the product of an in situ reduction of cobalt-2. And so that told me that, that ligand was just too reducing for cobalt. And so I did some chemistry on the ligand to try and make that central carbanion less reducing. And it's just, putting aryl oxides or alkoxides on each of the ligand arms. And I did this reaction so many times, just marching through ligands, finding what might work. My first bit of success came with the phenol derivative, which was actually pretty early on in my exploration. And so this is the first dialkyl cobalt complex, and this was, obviously very exciting. But you'll notice a pretty significant issue here, that it has a pretty significant bend in it. So I made a series of these molecules, and so the chromium, which is chromium complex, which has the most oxophilic metal, it actually makes a metal oxygen bond. And the zinc, which is not particularly oxophilic, it has a linear geometry. And for manganese, iron, and cobalt, there's no metal oxygen bond because it's a separation of like 2.5 angstroms, but there is a movement in the direction of the oxygen atom. The problem is that metal oxygen bond is so weak that the molecule is going to distort in any way possible to gain some sort of stability. So like I said, I just marched through a bunch of ligands and tried to find one that worked. And ultimately what worked was a naphthol derivative. And really the key factor for success here is intraligand interactions. So there are a lot of edge to face pi interactions, and as well as CH3 pi interactions. The molecule itself, I think it's pretty aesthetically pleasing. It crystallizes an R3 bar, and the cobalt atom sits on an S6 symmetry site. So it's ideal for the electronic and magnetic properties. Now, as for understanding those properties, I think a good place to start is with the ab initio calculations that our computational collaborators carried out. So if you start with the free ion, we have a quartet F and quartet P states. And if you just consider the effect of the ligand field, then you do get the expected ground state, where you have 4 electrons in that bottom set of e orbitals. But because the ligand field is so weak, once you include inter-electron repulsion, that's when you get the non-off-bow ground state. So just as a reminder, normally we think about inter-electron repulsion as determining high or low spin, but in this case, the electronically crowded ground state from just ligand field considerations, we can gain some stabilization by exciting that electron to that next set of e orbitals, but having a less electronically crowded configuration. Then the final perturbation is to consider spin orbit coupling, which is better shown here. And again, because this is a relatively simple system, the splitting of these energy levels is really only determined by the spin orbit coupling constant of the cobalt atom, which is exciting because that means that, if we prove that this is what the magnetic microstates look like, this is the maximum magnetic anisotropy that you could get with a 3D transition metal ion. So from the calculations, I would say there are three things to confirm. One is the non-off-bal electronic configuration. The second would be the ground M sub j state of 9/2, and then finally the magnetic anisotropy, which we can just confirm by looking at the energy separation between that ground and first excited M sub j states. We were contacted early on by Jakob Overgaard at Aarhus University, and he's an expert in crystallography. And if you take sufficiently high resolution data sets at low temperature, and you can get really high resolution electron density maps, which he then modeled to pull out the electron density at the metal centers. And he did this with a series of our molecules. And so for the cobalt complex, the key takeaway here is that the two sets of e orbitals have the same electron density. So this is direct confirmation of that non-off-bal filling. As for the magnetic properties, it's actually not a particularly interesting plot here on the left. So this is magnetic susceptibility times temperature versus temperature. And because it's a pure M sub j 9/2 ground state, it's a pretty simple plot. Although I do want to point out that our computational collaborators are great, and yeah, the line there is simulated data from their ab initio calculations that they sent us before they ever saw the experimental data. But because it's such a pure ground state and it has such large separations between that first excited state, even at room temperature, we don't get much information on the excited state. And so for that, we have to turn to spectroscopy. And again, this was something, I contacted Joris van Slageren, who's an expert with this technique. And what we're looking at here on the left is far IR spectra at low temperature and applied magnetic fields. And on just the raw spectrum, you don't see a whole lot because the vibronic transitions drown out the magnetic transitions. And so we divide the applied field spectra by the zero field spectrum. And so only the transitions that move in a magnetic field show up in this plot on the right. And so that feature at 450 wave numbers is the transition from M sub j 9/2 to 7/2. And that happens at 450 wave numbers. And that puts us in really good company. So this is the largest magnetic anisotropy reported for a transition metal complex. The previous record holders are there on the left. And we're pretty similar to the cobalt atoms observed by the IBM group. And that's because, again, once you have this ideal geometry, your magnetic anisotropy is really just determined by the spin-orbit coupling constant of the metal center. And so, like I said, this is magnetic anisotropy near a physical limit. And as for the dynamic properties, there's probably too much to go into right now, but I do want to mention that there's kind of a shift in how we look at things in the field of molecular magnetism. And I'm happy that I was able to contribute to this adoption of a new model for magnetic relaxation. Basically, magnetic relaxation is attributed to various transitions, either that M sub j 7/2 state or various vibronic mediated pathways, or a quantum tunneling transition. And those are all shown in the arrows on the right there. And the thing I was happiest with this modeling was that I was able to take values from the spectroscopy, and I had very few fit parameters, and I was able to get very good agreement between the fit and the data. And here you can see the different contributions from the different relaxation pathways. So in conclusion, like I said, a lot of this project was a synthetic effort, and it was very exciting. This is the first dialkyl cobalt complex that was isolated. But for magnetic properties, really all we care about is this central moiety. Yeah, I mean, because it's such an extreme weak ligand field, this behaves like a lanthanide. It has maximal orbital angular momentum for a transition metal. It has a non-off-bal electronic structure, and that yields an exceptionally high magnetic anisotropy. And so with that, thanks to my advisor, Jeff Long, as well as, the rest of my group. And I had a great team of collaborators that really helped bring this all together. So with that, I'd be happy to take any questions. Thank you.